When we write an equation like this, we're describing a chemical reaction. We're saying 1 mole of H2 gas reacts with a half a mole of O2 gas to give H2O liquid. So it's giving us a lot of mole relationships. It's telling us what the reactants are and what the products are. Now, we've seen in this chapter that reactions can absorb or release energy. If bonds are made during a chemical reaction, energy is released. And if bonds are broken, energy is absorbed. And often those two things are going on at the same time. We can write an additional part of this equation. Now I don't have to put the per mole there. I could, but I don't have to. If I don't put it there, I'm telling you that when 1 mole of H2 reacts, 285.9 kilojoules of heat are released. So the minus sign means released. And when half a mole of oxygen reacts in this reaction, then minus 285.9 kilojoules are released. You can use this as a conversion factor between moles and heat in a chemical reaction. For example, suppose I have a raindrop, which weighs about this many grams. And I want to know if I form that much water, if I form that much water, enough to make a raindrop, out of hydrogen and oxygen reacting, how much energy is going to be released? Well, if I look at the link that I have here, it tells me 1 mole of water is 285.9 kilojoules released. So I should change into water, moles of water. If I put in the molar mass of water here, I now have moles of water, and the thermochemical equation, which is what this is called, a regular chemical equation with a thermal part, a heat part, it tells me that for every 1 mole of H2O, I am going to get 285.9 kilojoules released. Now I either can leave the minus sign in, because the minus sign means released, or I can write the word released. They both mean the same thing. So I pick up my calculator now and I'd say 0.05 divided by 18.015 times 285.9 is going to give me how many kilojoules of heat would be released when you form 1 mole of H2O. For that reason, this reaction is called a formation reaction. We're forming 1 mole of this, and this is called a formation. Any reaction where you're forming 1 mole of a compound will be a formation reaction. And you're forming it from its elements in their most stable forms. Okay, here's a definition of a formation reaction. I have a little bit of explaining to do. I mean, what do I mean? Elements in their most stable forms. Well, when you have hydrogen, its most stable form is H2, gas, at room temperature and room pressure. There's a lot of elements that are gases. H2, that's the most stable form for hydrogen. O2 is the most stable form for oxygen. N2, the most stable form for nitrogen. F2 for fluorine. Cl2. Those are all the most stable forms of these. Notice that they've got a 2. Now, they're diatomic, we say. The most stable forms of a very few elements are liquids. You probably know mercury is a liquid at room temperature and room pressure. So I put a little L there for liquid. And the other one is bromine. It is a liquid at room temperature and pressure. So these are the most stable forms of these solids. Everything else So if you're going to write a thermochemical equation that's a formation, you've got to have the reactants that are elements in these forms. Now there is one special case in here I'd like to mention. There are some elements that have more than one solid form. For example, carbon. It can be graphite, or it can be diamond. And it has a couple of other forms too, but these are the two most stable. In graphite, the carbon atoms are arranged like the corners in chicken wire. They're put together into little hexagons. And then this repeats forever. So you can keep on writing hexagons after hexagon here. And that's what graphite looks like. Diamond, the carbons are tetrahedral. And you keep on hooking tetrahedral carbons to each other. And you keep doing that forever. And that's what a diamond looks like. In graphite, you have sp2 hybridized carbons. In diamond, you have sp3 hybridized carbons. Now I'm bringing this up because so that you understand why there can be two different solid forms of the same element. And one of these is more stable than the other. And it turns out to be graphite. Graphite is more stable thermodynamically than diamond is. So when you talk about the most stable form of carbon, you mean graphite. That would be sort of an A student thing to know, that graphite has more than one solid form, and that, or carbon has more than one solid form, and graphite is the most stable. So let's practice this idea of writing down a formation equation. Suppose I want to write the formation for this molecule. This is a liquid at room temperature and room pressure. It's dimethyl sulfide, and it gives the sea its smell. So when you smell the ocean from like 1.5 miles away, you're really smelling this molecule. Your nose is especially sensitive to smelling sulfur compounds. They're involved in decomposition, so that's a survival thing. If you smell sulfur compounds, there's protein breaking down, and your nose is telling you, don't eat this because it doesn't smell good. But this is not a bad smell, the smell of the ocean. Let's write the formation equation for it. First of all, in a formation reaction, I have 1 mole of the compound that I'm interested in. And then I'm going to take all the elements that are in here, C, H, and S, and I'm going to put them in their most stable forms. So with carbon, its most stable form is graphite. And I could just write solid there, or I could write graphite. The most stable form of H2 is H is H2 gas, and the most stable form of sulfur is sulfur solid. You could, some people will say, well, now wait a minute, sulfur also has multiple solid forms, and there is one that comes in necklaces of 8 sulfur atoms that's solid. So you should really be putting S8 solid in there. But we can go ahead and do this. There's no problem with doing this. So when I look at this now, C plus H2 plus S, it doesn't balance, right? I need to have 2 carbons. Because there are 2 carbons in this molecule. And I've got 6 hydrogens, so I'm going to need to put a 3. And there's only 1 sulfur, so I can just say plus S solid. So this is what my formation equation for this looks like. That's always 1 mole that I have here. I don't know what the delta H for that is, some number. Now, with formation reactions, you can abbreviate the entire reaction. And you're going to see on this worksheet people abbreviate these reactions this way. Instead of writing this reaction out, they'll write it in very compact form. They'll write delta H of formation for liquid water is minus 285.9 kilojoules per mole. They'll write this and it means that equation. So what you have to do is go ahead and write out the equation the way we just wrote this one out to get the full thermochemical equation whenever you see this. For example, if I have, let's do another one. Let's suppose I have peroxide, and I have a problem that has a thermochemical equation for peroxide in it. And it tells me delta HF, the enthalpy for the formation reaction, is minus 187.6 kilojoules. And I need to write a thermochemical equation out for that. All right, first thing I'm going to do is I'm going to write out the product as with a 1 in front of it. I have to keep a 1 in front of it. Then I'm going to look at the elements that are present. We've got H and we've got O. Then I'm going to put them in their most stable forms. The most stable form of H is H2 gas. The most stable form of O is O2 gas. And then I am going to add them up, and I'm going to make sure this is balanced. And it's balanced just the way it is. So when I write just this, and I tell you it's for peroxide, it's an abbreviation for this. And you have to write it out this way in several of the problems that you're doing on this worksheet. It's not the whole problem, but it's a big part of the problem that you have to write out.